Hugh O'Brien, who is joining us, and we're so thankful to have him here. And he can give you an overview of Finland and the diamond situation in Finland, followed up by, I believe, Roy, and then put together by Mr. Doyle. Good friend and good diamond person. So, glad to all have you here. Enjoy your little meal, and we'll be on the property tomorrow taking a very close look at what we're doing.
Excellent.
Hugh?
All right. Well, yeah, my job is kind of to set the scene for Roy, I think, and just talk about the sort of basic story of diamonds, a little bit about the diamonds in the world, and then narrow it down to talking about this area that we're working in here. So I thought I'd start out really basic here by showing you the planet Earth, okay, and a cross section, so that what we're always talking about are these. We're using the word mantle. So I just wanted to bring up this point that the mantle, this is where the rocks are coming from that contain the diamonds. And diamonds are actually just transported to the surface by these volcanoes that we call Kimberlites, and we're going to talk about those. But I just wanted to say that this word mantle, I'm going to be using that word quite a bit. And so does everybody understand that there's a sort of a plastic zone, which is the mantle where the rocks are actually hot and moving, and then there's the crust, which is rigid on top of that. Okay? And these plates are bumping into each other or crashing underneath each other. And the diamonds are coming from the mantle, but they're being transported into the crust. Yeah. So where do we look in the world to look at diamonds? And this is it's called a lithosphere thermal thickness map. It's basically that hard crust that I was talking about. And those plates that are rigid and they're moving around. And where are they thick? The thickest parts then are these numbers here represent the depth of that thick part. It's not just the crust, but it's the part that's rigid, okay? And there are certain places on the planet where you get these very deep, rigid pieces, like here in Russia, Yakutia, of course, and we know there's lots of good diamonds there. And okay, it's actually not quite as thick in South Africa as it probably used to be. West Africa, Brazil, obviously North America, India, and Western Australia. Actually, there aren't any good diamond deposits there so far that we know.
But Argyle was where?
Argyle is up here. Yeah. But again, deep, but not maybe quite as deep. But anyway, it's these rigid, and if we look at a real cartoon version of that, we need to have these very rigid bodies, and they're basically floating around in this fairly warm mantle. Diamonds aren't going to survive in these warm areas, so it's these cold, old pieces of mantle is where we're looking for diamonds. Okay, and that's why you saw in there that one of these big areas that's cold and old is this part of the world, Finland, and up into the Kola Peninsula. And actually on this map we've got a light color here just because they're covered with sedimentary rocks, but actually these same sort of rocks are underneath here as well. And what I'm going to show you now is a transect. Again, maybe I should orient you a little bit here. So we're now looking at the Kuusamo North deposit. There are Kimberlites also, Kuusamo South. But I'm going to show you a transect which is about 1,000 kilometers long from Kuopio all the way over to the Lomonosov mine in Russia. And first we can look at the ages. So in Finland we've got these Kimberlites at 600 million years. A group from Lentira, Kuusamo, at 1,200 million years. The next batch, these were found by Sunrise Diamonds at about 760 million years old. And then we've got dates on the wolves, so they're about 700 million years old. So it's kind of an odd age actually for Kimberlites in the world. They don't exist that many places at 700 million years. And then there's this large group of rocks, including all these large intrusions of cyanides and things at 340 to 380 million years. So it must have been a very large mantle plume here, and somehow those Kimberlites are related to that as well. And of course, Roy can tell us all about the grid over a beer or something. I don't have any pictures from there, but I do have from Lomonosov. And this is just to impress you that there's some data out there. Okay, but it's really just to show that we have, again, this is the same profile. Sorry. This is the same profile, and I've got these piercing points through it, these stars, and that is represented here by our data sets. So we've taken minerals that are coming from the mantle, and we're able to actually calculate the depth, and in this case I'm looking at the magnesium number, but I'm able to get an idea of the composition of the mantle from about 75 kilometers to about 275 kilometers down along that transect.
This is getting minerals out of the Kimberlites and measuring the chemistry.
Yeah, I actually, yeah, it's a little bit backwards. I've got some other slides about that, but okay. And so what we can do when we turn that data into a nice cartoon is that here we are, again, looking at that same cross section. And here we are at North Kuusamo. So there's a zone of, this says diamond in. So this is the sort of mantle section that we see. Remember that diagram I showed with these really deep roots? This is exactly the sort of deep root that we're talking about. And there's a very large zone then, and this is again going from Kuopiokavi to North Kuusamo, where there's diamond stable. There's quite a large zone there. And this is what the data from these minerals are telling us. Then we get into this kind of Luxor rift, and then back into what looks like very similar deep mantle, Arkhangelsk and Grib. So what we'd say is that the mantle we're looking at here in this part of the Finnish side is actually looking very much like the mantle on the Arkhangelsk side. And we know that there's some serious mines that have sampled that mantle and found those diamonds. So it's a similar mantle. There's no reason we shouldn't have similar sort of diamond sources. We just have to find the right kimberlites that have brought those things to the surface. I'll just show you some pictures of some serious diamonds. I was traveling in Yakutia, and these are just some samples, about $20 million worth of diamonds laying here. And actually, they don't normally take you into the picking room like this, but this is at the time it was worth about 20 million, and that one stone was worth about 5 million, because it was at that one, this biggest octahedra here. So just the fact that these Russians have been producing some really wonderful stones for a long time. The ones that we've got so far from Finland, well, we don't have nearly as much material processed, obviously, but these are diamonds from the Kaavi-Kuopio area. And some that are that's about 1 centimeter in size, the biggest one that was there. So definitely there are diamonds in Finland. Actually, if I ask a lot of Finns about this, they don't really know that there are diamonds in Finland.
It's okay, there's no diamonds in Canada either.
Is that true? They're all brought in from somewhere else?
Well, that was before they went into production. That's what Canadians thought.
That's what the beers promoted.
Yeah, okay. Yeah, and it's the same story here, but okay, there's been a long history of this going on here, but still, the Finns, I don't know, they haven't, not everybody's aware anyway. And we even have some samples. This is from Lahtijoki. This is an eclogite, and you've got some nice little diamonds sticking right out of it. And I didn't have the forethought to bring it. I had that little sample with me, so you can see some nice little octahedra in the eclogite. That's one of the main rock types that contains diamonds. And just one point about how diamonds are formed. We think that it's the process of fluids coming up from, again, this deeper part of the mantle into this stable mantle material, fluids that are then probably from methane into diamond. So it's an oxidation effect. Methane comes in and comes as a fluid. And why do we think that diamonds are coming in as a fluid and precipitating from a fluid? Well, this is kind of the reason. If you look at cross sections of diamonds, you can often find these kind of these are cross sections, cathodoluminescence. So you use a special light to shine on them, and you can see the growth rings, right? So these things have had a core, and then they've been resorbed, and then they've been growing again in the core. So that's the way diamonds are growing in the mantle. There's fluids coming in, there's some growth, then there's some time when the things start to dissolve again, then they start growing again. And that just analogy with that would be, this is a hailstone I just grabbed it from the internet, but even here you can see that you had a seed crystal, and then you had a layer, and then this layer got partly melted, and then the next layer got deposited on it. So it's fluid related. That's how diamonds are formed in the mantle. And another thing about real diamonds is the fact that most of them are actually quite old. I don't know if you've heard about this, but the fact is that obviously the things that are being made today, the man-made diamonds, are very young. So do you want to give your wife a diamond that's 2 days old, or do you want to give her something that's 3.8 billion years old? There's a lot of different ages, but and this is the age range from 3.6 to 1.2 billion years. And there's no way to date a diamond itself. But if you've got inclusions inside the diamond, like this little pyro grade, you can get an age off of that, or a number of those grains that you have to put together. Or often there's sulfide inclusions in some of the poor diamonds, but again, you can use those to get an age from the diamonds, and that's where some of these ages, including the sulfide ages, are coming from here. So diamonds have been around for a long time. The Kimberlites that bring them up, and I'm going to talk about this next, are actually much younger. So the diamonds are just incidental passengers, and have been formed a long time ago. And then the Kimberlites bring them along when they erupt. Just a couple words on diamond exploration. So economic ore can be as little as a few carats in 100 ton. And what does that mean? That means like the fingernail on your pinky in a cubic meter of rock, or the weight of a €2 coin in 100 tons of rock. That's ore grade. Can be ore grade. Depends on the value of the stones, of course, but that's the point. So the diamonds actually in the kimberlite, there aren't that many. They're actually spread out pretty far in the kimberlite itself. So if you're going to try to find the kimberlite that's containing diamond, you're going to have a hard time finding diamonds downstream from the kimberlite because they're so rare. But luckily, the rocks that come along with the diamonds have these specific kind of minerals, like these chrome diopsides and these chrome pyropes and these picroumanites. And there are a lot of those compared to the diamonds. So when we go exploring for diamonds, we're actually not looking for diamonds in the till samples or the sediments down ice. We're looking at things like chrome pyropes, picroumanites, magnesium ilmanites, chromites, particular kind of chromites, chrome diopsides, and yes, in the perfect case, you might find some diamonds. We did find one diamond in Lintia or in the till. So it can be, it is possible, but mostly we're looking for these indicators, and in particular we look at pyropes, because pyropes can tell us a lot about the source of the rocks. I'll get into that in just a little bit. But I was talking about up ice, and I should have explained that if you've got a kimberlite, here's our kimberlite pipe, and we've got ice moving in this direction, and all of Finland has been covered by ice, so, like we were saying in the car today, 3 kilometers of ice over our heads 20,000 years ago. So we had ice that was then dragging sediments along. The ice is running along the base of the hard bedrock, and it's pulling material along with it as it's scouring along the ground. And so you wind up with a plume that ideally should actually rise up into the till. So this is the sediment that the glaciers left behind the till, right? And you should ideally see this sort of plume that's rising up in through the till package. It's not always so ideal. I think you'll show another diagram. Roy's going to show some more diagrams, but what we do is we take lots of samples and we basically figure out where the most indicator minerals are, these minerals that are coming from the mantle, and then draw our diagram and figure out where the source is. This was actually the reverse. We had a PhD student that knew where the kimberlite was, took samples down ice just to show how the plume looked. This is in Kaviquopio, and this is up here in Kuusamo. And again, you can see that the indicator train points you right towards the body, which is here in both cases. Okay, but it's after the fact. We already knew it was there. But this is how these were found in the first place when the exploration company were here doing the exploration. Okay. And then a little bit about diamond prospectivity. So I told you about these minerals. These are coming from the mantle. They're not typical minerals. They're minerals that are coming from rocks that are from very deep. And we can actually tell an awful lot about the composition of these minerals about that mantle. Does it have the possibility? So even before we find the kimberlites or anything, we find the minerals in the till, we can analyze them and get an idea about whether there's actually mantle there that has diamonds in it. And one of the, again, I go back to these minerals that we use a lot, and one of those is, these are pyro inclusions, so garnets, magnesium garnets. We really use this a lot. And I'm just gonna show you data from, these are actually inclusions in diamond. Okay, so we analyze the inclusions and we plot them on a diagram of chrome versus calcium. So this is a plot, you're going to see a lot. Roy's going to show you this diagram quite a bit. And, okay, just remember these numbers, G9, G10, and this word eclogite. So if we analyze, when we have analyzed these inclusions, we come up with compositions in this field, compositions in this field, and compositions in this field. So if it's an eclogite-related diamond, we've got eclogite inclusions in the diamond. We've got G10s and G9s. Obviously, G10 or eclogite are the two main, so it's Hartsbergite is the name of the rock, and eclogite are the main source rocks for diamonds around the world. So if we find these garnets in the till, we know we've got something, okay? And that's, Roy's going to show you lots of not lots, but some diagrams where we've got lots of these kind of grades. So G10s are the important one for eclogite. All right. And then just, something about the kimberlites themselves. No human has ever seen a kimberlite erupt, so we actually don't know what they look like when they erupt. So this might be an example. This is a Mar eruption in Alaska, 1977. It might be close to what a little kimberlite looks like when it erupts. This one is 7 hectares in size. That would actually be a fairly large kimberlite. And the models that we've been using, and I think this is, okay, this is the bulk of the kimberlites. We have this sort of carrot shape. And I think if any of you have been working in the diamond business, you've seen these carrot shapes. If the top of the kimberlite is still there, there's a crater top. The diatreme is this massive TKB, we used to call it, toughest city kimberlite. And then the dikes and the sills at the sort of deeper parts of the body. And here, if you look at Ekati where they mined them out, I mean, you can see that the shape, of course, this is bigger than the pipe itself, but that's the shape because they followed the pipe down into the ground. Right? And they probably were quite explosive eruptions, and I guess you wouldn't have been one to be standing too close to these things when they're erupting. And they're obviously very fluid-rich magmas as well. And then another example, I visited this in July 2001. This is Mirny in Yakutia. And we're talking about a 500-meter pit, so this is a huge hole. They basically had to stop because, well, the town is right here. And 500 meters, that gets to be a very difficult hole to keep open. So now the whole operation is underground. But to get the size idea here, I'm going to show you this spot here next. So these are 30-ton trucks coming up this little path. This is an enormous thing. So the value here is enormous to put a hole in the ground like that. And so that's, of course, what we would be after. And the explosive power of these things is really impressive. This is a piece of this mantle that I've been talking about. So this is a olivine-rich rock with garnet and clinopyroxene in it. And it's, it's what, 80 centimeters in size. This thing has been brought up by the kimberlite. So this came from somewhere around 150 kilometers down, and the magma just brought it along to the surface. And yeah, Likabon, of course, had decent diamonds in it too. So. And the very happy geologist picking up some big chunks of peridotite from the mantle. Okay, so now let's zero in on our stuff today. Again, I've gone through this. Actually, I didn't show you this one before. There's another older kimberlite at Kussamo. Lots of little diamonds. They're not very nice, but there's lots of them. Then again, this Kostamuksha Kuhmo Lentier dikes where we worked a lot with European diamonds. These 760 Kuusamo, this should be southern Kuusamo dikes or pipes, and then the Kavikopio. Now, what I don't have on here yet is I didn't put on here yet is the wolves, which we'll show in a bit. And again, the pipes this is probably like Canada in a way that we don't have a lot of sediment cover in the area. In Finland, we have mostly these sort of granite basement. So the pipe size is usually in these sort of areas not that large. And here's a 100-meter scale bar. So the biggest pipe is about 4 hectares in size in Kamikopio. But the sort of typical intrusive and extrusive types of kimberlite there. And the best grade so far is 40 carats a 100 ton from the Latioki pipe. So whether that ever moves forward or not, we don't know. But at least it's owned by the Conroys, Carillion Diamonds Resources right now. But a little bit closer to home, these are the South Kuusamo pipes. We can see these are all textures that tell you that there is the diatreme fascia. Remember I said the carat part. And there's been a lot of discussion whether or not there could be any of the carat part left in Finland. Maybe there's been so much erosion that we're only talking about the very deep root zones. But when they discovered these kimberlites, it was very clear that at least at 760 million years, these things had erupted, and there's still the upper part of the pipe, or the diatreme part of the pipe still existing. So I mean that's good news. There hasn't been so much erosion that we're only going to be looking at the very bottom parts of these pipes. And then to just transport you over to the east here, about 500 kilometers east of us, are these Archangel diamond pipes. They're actually all in a row. These are now kind of just set here in an arrangement just to show them. But the point is that actually there are some very large pipes. That's about 1 kilometer long, the one pipe. Unfortunately, that one doesn't have any diamonds in it. But Karpinski, all these, Lamnisovia, Pionierskaya, so Arkhangelskaya, I've got a better picture. Arkhangelskaya, well, this is Karpinski, and Arkhangelskaya is just over here. And they're all 3 being mined right now, with ore grades around 1 carat a ton, down to about half a carat a ton. And this was in 2007. I actually was there in 2011 too, but I didn't find that picture. But anyway, actually the kimberlite here, the kimberlite starts here, and then these are bedded sediments. So the sediments that they're intruded into are the same color as the kimberlite. It's like when you're in the pit, you can't. It's really hard to see what's what. So the tufaceous part of the top of the kimberlite is looking very much like the surrounding sediments. And these are just some of the nice diamonds that they, again, let us go in and have a look at. And this is probably one of their biggest producing mines now from the Alrosa company. These pipes in Archangel. And they're spending a lot more money too in exploring in the Carillion area. So they're certainly thinking there's a lot of potential in the area. Okay, so just some pretty pictures of diamonds. Then just a couple to lead into Roy's talk, because we want to look at North Kuusamo. And these are thin sections. So what geologists often look at are these very thin slabs on a piece of glass. And then you look through the rock, you can see a lot of detail that way under the microscope. But just a couple typical samples from White Wolf. And one of the things you see right away, there's a pyrope. So again, these pyropes that I've been talking about that are very important for knowing the mantle conditions. And this is the mineral olivine, and practically every one of these olivines is actually coming from the mantle. It's not a phenocryst from the magma, it's actually a piece of the mantle rock. So this tells us that there's a very large quantity of mantle material that's been ground up by this kimberlite. And of course that's a good sign. If there's no mantle material, then we're not going to have a very good chance of producing diamonds. And then this sort of breccia texture. So this is the sort of rock I think we'll get to see at Grey Wolf. It looks very much like that. So lots of, some class of cutting rock, but most of the stuff here is actually fragments of olivine, which has come straight from the mantle. And just leave you with this. So we've got some winter drilling and some nice pieces of kimberlite here, and a couple of those pyropes again that you can't see too well on that picture, but we won't have any. Well, we'll see what we find out there. Probably find some nice garnets as well when we dig this thing up tomorrow. So that's my part. I'm gonna, I think, just roll right into Roy's here.